In the previous module, we have learned about signals as functions of one or more independent variables. Now that we are familiar with signals, let's play with them. In this module, we are going to learn about some basic operations that we can perform on signals. In order to understand these operations, let's consider an example of a signal. Consider the signal that is being shown on the screen. This signal takes the values like this. The signal is 0 from minus infinite to 0. It takes the value 1 between 0 to 1. The signal decreases linearly from 1 to 0 between 1 and 2. Let's consider this simple signal. The simplest possible operation that we can perform on this signal is shift. We can consider this signal and try to shift this signal. The shift can be performed either along the independent variable like this or along the dependent variable, that is upwards or downwards. Let's analyze each of these cases one by one. Let's try to shift this signal, say for example, upwards by 1 unit. So the new signal will look something like this. Now this signal is being shifted upwards by 1 unit. So the new signal will take the value something like this. You may observe that each of the values here in the new signal gets added by a constant, that is 1. Let me mark the axis here. That is t. It is again t in the negative direction. The value here is 2. Here it is 1. The time axis is 1 here, 2, and so on. You may see that it is the same original signal which is being replicated here, except the DC shift of 1 or a 1 constant that is being allotted for each of these values of the original signal. Therefore, I may express this signal in terms of original signal as x of t plus 1. This indicates that the new signal is simply the original signal, but with an additional value of 1, just because it is being shifted upwards by 1 units. Similarly, we can shift this signal downwards. Let's try to shift this signal downwards by 1 unit. The resultant signal will look something like this. How did we obtain this signal? You may see that this is the original signal. The same original signal is being shifted downwards by 1 unit. So this line will come here. This line will come here. That has come here. Let me mark the axis. That is 0. This time t. This value, as this signal is being shifted downwards by 1 unit, this is going to be -1. Therefore, the original signal can be expressed as x of t minus 1. What does this indicate? The new signal is the same as that of the original signal, but with a DC shift of minus 1. That means the signal is being shifted downwards by 1 unit. Now, in both of these operations that we have performed so far, we have performed all these operations along the vertical axis. That means along the dependent variable. Let me write that. So the operations are performed along dependent variable What are those operations? The first operation that we have performed is upshift. And the second one as downshift. Now, as we have seen that these operations have been performed along the dependent variable, similar sort of operations we can perform along independent variable, that is horizontal axis, which is time. Let's study these operations. Let me consider the same signal. Now, let's suppose I need to shift this signal leftwards by 1 unit. How the new signal looks like? Let me draw that. As we are shifting this signal leftward by 1 unit, instead of starting it at 0, it will start from -1, just because we are shifting the signal leftwards by 1 unit. Therefore, this will begin from -1, so somewhere here. And so on. Let me mark the axis. It is 0, 1, -1, this is t. Now, how can we express this new signal? Let's observe this new signal. You may see that the signal that is being newly obtained here is simply the signal that was there here. That means the newly obtained signal is simply copied from position higher in the original signal. See here, this line is simply copied here. This line is simply copied here, and so on. Therefore, a signal here is obtained from a position higher in the original signal. That can be expressed as something like this. So the new signal is obtained as a position higher in the original signal. Note that we are making the change in the argument just because we are performing the operations along the independent axis, independent variable, that is time. And the signal that was supposed to start from 0 is now being starting from -1. Therefore, we may say that signal is being advanced by 1 unit. In order to indicate that we represent that as x of t plus 1. This indicates that the signal has been advanced by 1 unit. As we may see that this signal is being obtained from the signal a position higher in the original signal. Similarly, let's try to shift the original signal rightwards. So if we try to shift the original signal rightwards, it will look something like this. Now this signal is being shifted rightwards by 1 unit. So instead of starting from 0, it will start from 1. So the resultant signal will look something like this. Let me mark the axis. The axis being t. Here it will be 1, 2, and the signal will end at 3. Now you may observe here that the original signal that was supposed to start at 0 is now been starting from 1. So the signal that was supposed to start at 0th second, for example, just because this is time, now it is starting from 1 seconds. So there is a kind of delay which is happening in the signal. So that delay can be expressed as x of t minus 1. Again, here we are making change in the argument itself, just because we are making operation along the independent variable, that is t. In both of these operations, the amplitude remains the same. There is no change in the dependent variable. So in both of these operations, let me mark that we are doing all these operations along independent axis or independent variable. Independent variable. What are those operations? The first operation that we have seen on the right is the left shift. And the second operation that we have seen is the right shift. The left shift operation is also called as advancing operation, time advance operation. And the right shift is also called as delay operation. So far, we have done this shifting operations along the dependent variable and along the independent variable. We can perform other operations other than shifting. Let's see them. Consider the same signal. Now, another operation that we can perform on the signal is to scale this signal. For example, when we are working on electronic circuits, especially amplifier circuits, it simply amplifies the signal. The amplification means it will simply scale the amplitude of the signal. Those operations can be performed on this signal as follows. So if you try to amplify this signal by some units, say for example by a factor of 2, what will happen? This amplitude of the signal will get scaled by 2. So the resultant signal will look something like this. Here the 0 is multiplied say by a factor of 2. Here 1 is getting multiplied by a factor of 2 and so on. So the resultant signal will look something like this. Let me mark the axis. This is 1, this is 2, whereas the y-axis mark here is 2. Now suppose if I am scaling this signal by a factor of 2, I'll express this as 2 times x of t. What is that? The new signal is the same as that of the old signal, but it is being scaled by a factor of 2. So this twice of x of t indicates that the new signal is being the same signal as x of t, just being scaled by a factor of 2. Now the scaling factor can be less than 1. In that case, the signal will attenuate. So this operation, we may say that it is an amplification operation. Amplify. Similarly, we can attenuate the signal if we have the scaling factor less than 1. So the new signal will look something like this. Suppose we attenuate that signal, the original signal, by a factor of 2. So the value that was here as 1 will get halved. Therefore, the new signal will look something like this. What is the value here? The value here is 0.5. Why? Because this new signal is being obtained after scaling the original signal by a factor of 2. Therefore, this can be indicated as x of t multiplied by half. Remaining things, the axis notations remains the same. 1, 0 and so on. So this is attenuation operation. Both of these operations comes under scaling of the dependent variable. You may note that in both of these operations we are scaling the dependent variable. We are scaling the amplitude. Another operation that we can perform is flipping operation, meaning we can simply flip this signal upside down. So the resultant signal will look something like this. So we have simply flipped this signal upside down, the original signal upside down. The axis remains the same, 1, 2, and so on. How can we express this signal, the new signal? Well, you may observe that the value that was 1 here is getting flipped upside down to -1 here. Just because it is simply a mirroring operation along the dependent axis, along the vertical axis. So it's like simply keeping the mirror horizontally and simply looking at the signal being flipped upside down. Therefore, we are flipping this signal along the dependent axis. We can express this signal as minus of x of t. Why minus? Because the signal that was 1 here has now obtained a value as -1. The signal that was suppose 0.5 here has now got the value of as -0.5 and so on. So this signal is obtained after the operation of flipping. But this flipping is done along the dependent axis. Now, all these operations that we have performed so far, amplification, attenuation, and flipping, all these operations have been performed along the dependent axis, that is the vertical axis. Similar sort of operations we can perform on the independent axis. Let's see them one by one. Consider the same signal. Let's say I want to scale this signal along the independent axis. That means, say for example, I need to squeeze this signal or expand this signal. Let's take these operations one by one. I'm firstly trying to squeeze this signal. After squeezing this signal, after you can say it as compressing the signal, say by a factor of 2, it will look something like this. The axis being the same. I'm squeezing the signal. So the resultant signal will look something like this. Now, how have we obtained the signal? Well, you may see that this is the original signal. The resultant signal is simply the squeezed or the compressed version of the original signal, and it is being compressed by a factor of 2. But the compression has been turned along the independent axis. You may see here that the value that was here, say for example, this signal here, this line is now been compressed as like this. This line that was of this much width is being compressed by half unit. Therefore, this signal can be expressed as x of 2t. What does this indicate? This indicates the compression by a factor of 2. You may verify this by inserting different values of t. Say for example, the signal that is being present in the original graph at 2 is being present in the new signal at position 1. For example, this value is being present here. This signal is now being present here. So the overall signal is being compressed along the independent axis. This compression can be expressed as x of 2t. Why x of 2t? Because the value that was there at say t equals to t naught is now being present in the new signal at 2t equals to t naught. This implies the new signal is having the same value at t naught by 2. Therefore, the value that was present at 2 is now present at 1. The value that was present at 1 is now present at half, and so on. So here it is 1, here it is 0.5, and so on. So such operation is called as compression, or is also called as scaling along the independent axis, squeezing or compression. So we are simply squeezing this or compressing this signal. Similarly, we can perform expansion. Let me try to expand this signal. Let's take the expansion factor again 2. So the new signal will look something like this. This will be the new signal that is being obtained after expanding the original signal. So the amplitude will remain the same. These markings will be doubled. Now you may compare the original signal with the expanded one. You may see that this signal is now being expanded twice by a factor of 2. This signal is also expanded by a factor of 2. So each of these segments in the original signal is being expanded by a factor of 2. Therefore, we can express this signal as x of t by 2. Why t by 2? Because you may see that the signal or the line segment that is present in the new signal is obtained from the original signal that is present at half the location. The new signal here is present in the original at half the location. You may see here this point. Suppose for example this point here, this age point is present at half the location in the original signal. This point here that is here at 4 was present in the original location at 2. This point is present in the original signal at 1. This point is present in the location at 0 and so on. Therefore, the new signal is being obtained from the original signal that is being placed at half the locations. Therefore, the new signal can be expressed as x of t by 2. Why t by 2? Because, let me write that here, the signal, the value that is there at t equals to t naught is now being present at t by 2 equals to t naught. Therefore, it is present at t equals to twice of t naught. This operation is called as expansion operation. Expansion. The last operation that we would like to see here is the flipping operation. Now we are trying to flip this signal. Unlike in the previous case, we are trying to flip this signal along the horizontal axis. That means we are trying to keep mirror here. So this will simply flip from right to left. The resultant signal will look something like this. You may see that the new signal that is being obtained here is simply the old signal but being flipped along the horizontal axis. Therefore, this signal can be expressed as x of minus t. Why x of minus t? Because this is being flipped along the independent variable. Therefore, the change has to be made along the independent variable, that is t. This is nothing but the flipping operation along the independent variable, that is t. We'll see more on this in the next module. Thank you.